Thank you, Mr. Chair, for the kind introduction. I'm delighted to have the chance to present our work today. Good afternoon, professors and teachers. I'm Zi'ang Liu, a PhD candidate from the School of Aeronautics at Northwestern Polytechnical University. My advisor is Professor Xitao Zheng. I'm honored to present our work on assessing the effect of delamination damage on the residual compressive strength of aircraft composite laminates. My topic is organized as follows, focused on three areas. Let's start with the background and motivation. Establish appropriate design allowables is critically important for ensuring structural safety and reliability. For composite structures, determining the design allowables requires consideration of structure integrity, which encompasses strength, stiffness, damage tolerance, and durability. From the perspective of damage tolerance, our research aims to increase the design allowables for composite structures. Improving damage tolerance primarily involves assessing the residual strength of the damaged structure. Research indicates that composite structures can experience a significant reduction in residual compressive strength after impact loading. The composites have relatively weak interlaminar properties, making them susceptible to delamination damage on impact, which severely compromises their compressive performance. Furthermore, studies have shown that delamination defects account for a substantial portion during the manufacturing process of composite structures. Therefore, it's critical to investigate the influence of delamination damage on the residual compressive strength. The literature survey has identified that three key problems have not yet been adequately addressed. Firstly, how to select materials for aviation structures susceptible to delamination. And secondly, a more comprehensive analysis of the effect of delamination depth on residual compressive strength needs to be done. Furthermore, currently available methods such as zipping, three-dimensional braided stitching, and interlayer toughening have been found to demonstrate fairly significant improvements in suppressing delamination damage on a low-velocity impact energy. Moreover, these techniques can adversely affect the in-plan properties of the original structure. To address these challenges, we propose a research plan centered around three key aspects. Firstly, we will compare the effect of delamination damage on the residual compressive stress of different composite laminates. Subsequently, the influence of delamination depth will be investigated. Finally, in an effort to mitigate the detrimental effects of delamination on the mechanical performance of the laminates, we will explore the application of a discrete toughening strategy to suppress its growth. For the first part of our study, we selected four distinct materials combining two strength grades and two fiber orientations, designated sequentially as M1 through M4. Delamination damage was introduced by two methods. The first involved inserting a Teflon film at the midplane during the laminate manufacturing process to create a single delamination to simulate effects arising from production. The second method subjected the curved laminates to low velocity impact, replicating in surface threats such as hair, runway debris, or web spread. It's worth noting that this phase of the research was conducted experimentally. Analysis of the test stats on residual compressive strength for laminates with single delamination and impact damage led to two primary conclusions. Firstly, low velocity impact damage degrades the compressive performance of laminates more severely than single delamination does, especially for low strength unidirection composites. Secondly, in impact-prone or delamination-sensitive areas of aircraft structures, the use of high-strength fabric prepregs is preferable to unidirection prepregs for enhanced structural integrity. The second part of our research primarily utilized finite element simulation to investigate the influence of delamination depth on the residual compressive strength of composite laminates. A single composite laminate material was selected, and a finite element model of a laminate containing a single delamination developed in Abacus. The composite piles were modeled using solid elements, while the interfacial behavior was simulated with cohesive elements. A comparison between the simulation result and the experimental data showed consistent failure modes. Furthermore, the error in predicting the failure load was within 10%. Based on established finite element model, in the depth direction, the position of the delamination was varied. The computational results presented in Figure 7b indicate that the compressive failure load of the composite laminate exhibits a trend of initial decrease followed by an increase as the delamination depth progresses. Finite element simulation provides the explanation for this trend. The right-hand figure shows the simulated load displacement curves and stress nephrograms for different delamination depths. Let's focus on the blue curve, firstly, which represents the shallow delamination. At point A, the thin sublaminate wrinkle causing a minor stiffness reduction but no load drop. At point B, the thick sublaminate wrinkles result in a catastrophic load drop and loss of capacity. This suggests that the failure load is dictated by the thick sublaminate. Therefore, as the delamination deepens, the thick sublaminate becomes thinner, which reduces the overall failure load. Now please observe the red curve, which represents the deeper delamination. At point A, the thin sublaminate wrinkles first, causing premature global failure. The failure load is now governed by this thin sublaminate. As depth increases, the governing thin sublaminate becomes thicker, leading to an increase in failure load. Finally, attention is turned to the black curve in the figure, which represents the case where the delamination is positioned at midline of laminate. Due to the symmetric layout, the upper and lower sublaminates are nearly identical. They consequently underwent simultaneous wrinkling, leading to an instantaneous load drop. Notably, the failure load of this midplane delamination laminate shows almost no reduction compared to the undamaged laminates. In summary, the key findings from the above analysis are as follows. To begin with, the compressive failure load of the composite laminates exhibits a non-monotonic trend with increasing delamination depth, characterized by an initial decrease followed by a subsequent increase. In addition, depending on the depth of the delamination, the bearing capacity of composite laminates is governed by different sublaminar configurations. Finally, the delamination splits the composite laminate into upper and lower sublaminates. The effect of the delamination on the mechanical performance is minor under the critical condition where the load-bearing capacities of these two sublaminates are balanced, leading to their simultaneous failure. Last but not the least, we implemented a specific strategy to suppress delamination. Delamination damage incurred during actual manufacturing is not necessarily circular. Elliptical delamination is more prevalent. Our investigation revealed that an elliptical delamination is more critical when its major axis is oriented perpendicular to the loading direction. Small. Introducing toughening materials at the interfaces of composite laminates can enhance their interlaminar fracture toughness. To suppress the propagation of delamination in this critical perpendicular direction, ring-shaped toughening films was interleaved discretely between the piles of the laminate. As shown in the figure, the results from the low velocity impact and subsequent compression of impact tests are presented. It can be concluded that the discrete toughening strategy significantly enhances the residual compressive strength of the composite laminate by effectively suppressing the delamination growth perpendicular to the loading direction. Based on the investigation detailed above, the primary conclusion form are as follows. To start with, for locations in aeronautical structures that are susceptible to impact or prone to delamination, selecting high strength carbon fiber fabric prepregs is the more favorable choice compared to unidirection tape from a structural integrity standpoint. Additionally, the bearing capacity of composite laminates is governed by different sublaminate configurations depending on the depth of the delamination. Last but not least, the discrete toughening method significantly enhances the comparison of impact strength of laminates by restricting the propagation of delamination damage in the direction perpendicular to the loading axis. Next, I would like to introduce my research team. Institute of Aircraft Composite Structures is based on the School of Aeronautics in Northwestern Polytechnical University, located in Xi'an, Shanxi Province. We focus on the design, manufacturing, analysis of composite material structures, and aim to solve the key technology in the design and manufacturing of aircraft composite structures. That concludes all the content I wish to present. I sincerely welcome your valuable comments and suggestions. Thank you.